All right, now let's look at the next easiest case. What if the auxiliary equation has real roots, but there's some repetition there? So we see a root twice. So if we're solving a polynomial of degree n, it could have repeated roots. We could see the same thing twice. And then e to the rx, e to the rx, well, aren't two solutions. It's the same solution twice. We want a basis of n linearly independent functions, so we can't use anything twice. We wouldn't have linear independence then. So if a root r appears, now a real root, appears with multiplicity k, so k times, then e to the rx is one root, and then x e to the rx is going to be the next. And then we keep raising x to powers until we have k different solutions corresponding to the multiplicity k. So x to the k minus 1 is going to be the highest power we need. So this is a set of k linearly independent solutions in a basis of the solution space. So for example, if the roots are 2, 2, 2, -3, -3, 4, then basis would be e to the 2x, x e to the 2x, x squared e to the 2x. So we keep raising the powers until we have as many e to the 2x's as there are 2's, and then e to the -3x, x e to the -3x, and finally x to the 4x. If a root is not repeated, we don't need to multiply by x. But if -3 comes up twice, then the second time it needs an x. So I'm just making up those solutions. Let's start with a real differential equation, and let me choose one that has repeated roots. So let's solve y double prime plus 6y prime plus 9y equals 0. I'm choosing this because I know that r squared plus 6r plus 9 equals r plus 3 squared. So the root of -3 appears twice. So basis of the solution space is e to the -3x and x e to the -3x. So in other words, all solutions are something e to the -3x plus something x e to the -3x. Now, a question we could ask about this two-dimensional space of solutions is which solution has a certain property. So which solution satisfies y of 0 equals, let's say, 1 and y prime of 0 equals 0. Well, y of 0 being equal to 1 implies that c1 e to the 0th is just 1, plus c2 e to the c2 0 times e to the 0, that's going to be 0. So c1 equals 1. Well, that's easy. c1 is 1. Y prime of 0, well, I think I'd better figure out y prime of x first before I plug in 0, because we've got a little product rule going on here. So y prime equals negative 3c1 e to the negative 3x, that's easy, plus c2, derivative of the first times the second, plus derivative of the second times the first. So y prime of 0 being equal to 0 means that we have negative 3c1 e to the 0th is 1, plus c2. When we plug in 0 here, that part's going to disappear, and we've got c2 e to the 0th, which is 1, so c2. This equals 0. So if c1 is 1, then this says that negative 3 plus c2 equals 0, or c2 equals 3. So the solution satisfying y of 0 equals 1, y prime of 0 equals 0 is c1 is 1, y equals e to the negative 3x plus 3x e to the negative 3x. The end.